Follow Shadow Junior Twin.
Hello, everybody. So, ambitious goal. I put this up on my story yesterday, and I'm going to cover all of A-level computer science before paper one. Okay, we have 139 days to paper one on June 10th, 2026. So, quite a while, like almost 4 months, right? And it's going to be approximately around 40 videos to cover all of paper one and paper two, which means I'm doing around a video every 3-ish days. So if you do A-level computer science, and even if you were very confident, may as well watch a quick 5, 6, 7, 8, 9 minute video for all of the topics, because I'm going to be pumping these out and I'm going to get this done, and if I don't, then I'm going to delete my account. So we're going to start with paper 2, as I believe it's easier content. This is me trying to get this all done, but it's going to happen. So the first topic that we're going to cover, the first raw topic, is the pathfinding algorithms. A very, very fun topic. This also applies to decision mathematicians. If you do decision maths, this video is also for you. So we've got Dijkstra's and A-star, which are both great algorithms. And so let's start off with our definitions and what they do. So both A-star and Dijkstra's aim to find the shortest / a short path. This ties into A-star, but for Dijkstra's, just consider the shortest. It finds the shortest path from a node to another on a weighted graph, with the two having some distinctions, right? There's a distinction between A-star and Dijkstra's. They're not exactly the same, and there's some comparisons we'll make when we're answering different exam questions, right? So these distinctions then appear in short form questions, but to go over these distinctions, you need to define them both algorithms first, right? So A-star is a heuristic algorithm which builds upon Dijkstra's, which I will talk about later. But since A-star builds upon Dijkstra's, let's go over Dijkstra's first. Great algorithm. So I feel like the best way to go over Dijkstra's, like the actual algorithm on a graph, is to just do an example. But first, we'll just go through like the worded definitions, right? So given a start node, Dijkstra finds the absolute shortest path to every other node in the graph. So it does this by considering a node's closest neighbor until every node has an established distance from the start node. What does this even mean, right? Well, we're going to see this in a minute when we look at the example on the next page. But let's keep going through the definitions. Since it calculates the shortest distance to every node, so every node in the graph, Dijkstra's will calculate the shortest distance to it from a start node. One distinction from A-star is that it is less time efficient, right? If you're calculating the distance to every single node, that's going to take a long time. It's not as time efficient as A-star, which doesn't do this. However, A-star doesn't always get the absolute shortest path, and we're going to go over why in a minute, which means that Dijkstra's is more accurate. So there's a bit of a spectrum going on, right? We have accuracy, and we have time efficiency. And you can't have both, right? You can't have both. You can have one or the other. So you kind of have to sacrifice time efficiency for more accuracy. Let's apply to a simple problem and then a more complex past paper question. Ooh, big boy past paper question. So this is our graph, and we're trying to traverse from A to D. So the nodes will be given to us. We have A, B, C, and D. And we have the distance traveled being 0. We always set it like this. So what does this mean? We set the start node to distance of 0 because how far does it go from A to A? Well, it's going to be 0. It doesn't have to travel anywhere. And we set all the distances to all the nodes to infinity as we begin. That's just how we do it, right? So this is how we start the algorithm. And what we do is we consider the node that we start with. So we consider A. We consider this node. And we look at all its neighbors, all of the neighbors. And as you can see, A connects to B, C, and D. So it connects to all three. And then what we want to do is we want to add the weights from A to all of these nodes. So A to B has a weight of 2. So we cross this out, we write 2, and we write the previous node being A. A to D has a weight of it's a distance of 9, previous node of A. And A to C has a distance of 4, previous node A. It is important that you're crossing these out and not rubbing out. Crossing out shows that you're following the working out route and what you need to do to get all the marks. Like the mark scheme will have crossed out numbers in them to show that you've iterated through the program to get to the final distance, right? So then what we want to do is we want to select the row with the lowest weight. And as you can see, it's row B. So now that we have a new node and the lowest distance traveled to it is D out of the 2, 4, and 9, we can mark Y as visited, right? It is done. we visited A, we can cross it off. All the nodes have been visited from A, so it's finished. So now we've picked B, and we do the exact same process. Well, B connects to A and D, right? Well, we don't want to go back to A because that's the start node, so there's no point checking that. But is it lower than what D currently is? 2 add 7 is 9. So 9 is obviously not less than 9, it's the same. So we don't have to change anything. So we can mark B visited. So now what we want to do is pick the lowest distance traveled on the non-visited node. This is visited, this is visited. So the lowest weight or the distance traveled for a non-visited node is C. So we pick C and we look at all its neighbors. We don't want to go back to the original because why would we want to do that? But if we go from C to D, it has a total distance of 8, right? We have to add the previous node distance, right? Because A to C was 4, so we add 4. So we consider all the neighbors of C, and now has a way of 8 to get to D. So we cross out 9, write 8, cross out A, write C. And this is then fully visited. So then the lowest distance traveled or weight of a node that isn't visited is then D. We check all its neighbors. Well, all the neighbors are going back towards the start, so it's not going to impact any of the distances, right? So now we finished the algorithm because all 4 nodes have been visited, right? Meaning that the final distance from A to D, the minimum distance, is 8, and we have to work out the path, right? We're going from D, and then we go from the previous node. So we came from C, okay, because it has it here. Well, we're not at the start yet, right? We came from C. So how do we go from C back to the previous node? Well, C goes back to A, and A is our start node. So that's what we have to do. We have to backtrack our way until we end up having the start node being here, which is just A. Very simple traversal. So the distance traveled is 8, and the minimum path is A, C, D. Okay. We need to go over to GoodNotes to look at our exam question, because this is just a past paper Dijkstra's question. So this is an actual paper question from the previous years. I think this was 2023. I'm not too sure. And we're just applying the exact same thing, right? But we're just using it on a bit more complicated graph with an actual past paper question. So we're going from A to G, which is simple, right? We need to consider A and all its neighbors. That's how we start off the algorithm. So A to C has a distance of 2, previous node A. Then we look at A to D, distance of 10, previous node A. Then we look at the final neighbor, which is B. So it has a distance of 5, previous node A. Now you tell me, this is visited, so let's try to V. Which node has the lowest distance traveled which isn't visited? It's C, right? It has a distance traveled of 2. So we want to go to C and see what's going on at C. C's got 2 neighbors, one of them being A. We don't want to go back to the start. So we're only going to see if 8 makes a difference. So 2 add 8 is 10, but D already has a weight of 10. So we're not updating D at all. So C is now fully visited. Okay, now, what's the weight? What's the graph with the lowest weight, which isn't visited? It's B. Let's go to B. B has 2 neighbors, goes back to A. We don't want to go. We do not want to go back to A. But it also connects to E, which does not have a weight. We should be now set to 7. Previous node being B, right? Because that's the one we're looking at. So now B is fully visited because we looked at all its neighbors. What node has the lowest weight, which isn't visited? E. Let's look at E. E connects to G and F. The weight to G is 19. So we do that. 19. We're going from E. And then if you look at F, the total weight is 15. Going from E, sorry. So now E is fully visited. Weight with the lowest thing, D. So D has only one neighbor which isn't already visited, which is G. And the weight to get to G is 14, which is less than what we have. So we cross this out, write 14, cross this out, write D. Mark it as visited. Weight with the lowest distance traveled and lowest weight is G, which isn't visited. So we go to G, and we see that G connects to D, which is already visited, and E, which is already visited, so those are minimized. But it also connects to F, and it has an arc length, so F of 1. So this is 14. 14 added 1 is 15. Um, so it doesn't actually change it. So we mark this as visited. And then F, we mark it as visited too because it's connecting to already visited nodes, right? So this is our final graph, our final table. Dijkstra is finished because all the nodes have been visited. And from A to G, it has a distance traveled of 14, the final path of G. And then let's backtrack. See, we have D here, and D to A. Nice simple path. A to D to G, right? And as you can see, Dijkstra's will find the minimum path to every single node in the graph. Even though we're getting asked to traverse from A to G, it will find the distance to every node because it visits all the nodes and minimizes all of these distances, right? So let's go back to the PowerPoint and look at A star. This comment down here is a bit annoying, but doesn't matter. Let's get these up. So A star is a heuristic extension of Dijkstra's algorithm that finds an efficient but not always shortest path from one node to another, right? Well, first of all, what does heuristic mean? You might not have come across this word before, and I'm going to assume you don't have that baseline knowledge. Let's define it right here. It's just a problem-solving rule of thumb, right? Which you can then use to reduce the time complexity of a very complicated problem. If you really think about how Dijkstra's work, if you have a graph, let's say that represents, I don't know, London, think about all the tube stops in London, for example, or think about all the bus stops. There's probably hundreds of bus stops in London. And if you're trying to use Dijkstra's to check the distance between all the bus stops, that will take a very, very long time. So we're going to use a heuristic, an educated rule of thumb that should make the complicated problem a bit more easy to solve. And here we have here, this is therefore a trade of accuracy for speed. So it's going to be quicker, but if it's going to be quicker, then something has to be decreased, which is going to be the accuracy. So yeah, and this comment down here, this is where maths is useful. Everyone loves A star because there's a bit of maths in it. Because how are these heuristics calculated, right? So this isn't required. You do not need to know this. You need to know what a Hamiltonian distance is, but you do not need to know how to calculate it. But it's interesting, so I'm going to talk about it. So the heuristic in the A star algorithm is basically how far it is to go from the start node to the actual node in terms of Hamiltonian or Euclidean distance. But the Hamiltonian distance is just the changing coordinates. Like if you have a grid like this, and you want to go from this here to here, it's 1, 2, 3, 4, right? So that's quite simple there. But if you did Pythagoras, it'd be 2 root 2, which is Euclidean distance. And this route should extend all the way, but I don't have to do it in Google Slides. So Euclidean distance is much preferred by mathematicians, but some people like Hamiltonian distance because it's very easy, which I'm not a fan of. I don't like those people. So let's look at A star now on the exact same graph, except we are given heuristics, right? The heuristics are in bold above each thing. So we're given 6 for A, 4 for B, 3 for C, and 0 for D. D is going to be 0, even though it seems to be far away, because that is our destination node. That's the node we're trying to get to. We're going from A to D. Since it's the given node we want to get to, we set the heuristic to be 0, because it's the right direction, obviously, because it's the destination. It has to be the right direction. So what we do for A star compared to Dijkstra's is we want to try to find the node which has the lowest distance traveled plus the heuristic. Before, we just considered this, but now we're considering this here too. So let's actually start the algorithm. Remember, same thing as Dijkstra's. We look at all the neighbors of the start node, which are B, C, and D. The distance from A to B is 2. So we cross this out, right? 2, previous node A. A to C is 4, previous node A. And A to D is 9, previous node A. But we also then have to consider the distance plus the heuristic. Here it's 6. We don't really have to consider it for A because it's the start node, so we ignore that. 4, 3, 7. Would you look at that? 9 at 0 is 9. So the node with the minimum distance traveled plus heuristic is then B. So that's another one to select. We mark A as visited, right? We've already visited A. So B, we'll have considered all of B's neighbors, right? We don't want to go back to A because we don't want to go back to the start point. We're starting from A. So we consider D, 2 at 7 is 9. Distance traveled is already 9, so we don't update that. Nice and chill. And then C is the next node, which has the minimum distance traveled plus heuristic. So we look at C. Don't want to go back to the start node. So we check D. So 4 add 4 is then 8. So we cross this out. This is then 8. This is then C, right? So we mark this as visited. And once we get to D being the lowest node, which isn't visited, since it's the destination node, we stop the algorithm here. The minimum path, the minimum distance is 8, and the minimum path is D, C, A. The reason why A star is more efficient than Dijkstra's is because once you reach your destination node, you could have reached the destination node before you even got to B, for example, on a different graph. You just stop the algorithm. If it's the smallest thing you can consider, then how are you going to make it any smaller? Once you reach your destination node, you just stop. And that's why it would finish quicker than Dijkstra's, because sometimes it stops before it even checks all the nodes in the graph, if that makes sense. That might be more apparent in the algorithm we're going to go through in a second. So let's go through that now. Here is the question, so if you give that a read, we're obviously given all the heuristics and all that good stuff here, and we're given all the arc weights. This is the exact same thing as Dijkstra, except we now have heuristics, which are just kind of cool, which I of course forgot to write in. So let's do that together. So we have 90 for A, for C we have 43, B we have 80, D we have 70, E we have 20, F we have 8, and G, as you can see, is its destination node, which is cut out in the question, but we're going from A to G, is 0, because it's destination node. So let's go through the algorithm. We look at A's neighbors, being B and C. We write down its distance, 20 and 44. 20 and 44. So the previous node was A, previous node was A. We add these together, we get 100. We add these together, we get 87. Node with the minimum distance plus heuristic is C. As you can see, you see how B has a lower distance than C. However, we're not picking it because its heuristic at plus distance is higher. That indicates that C is moving in the right direction. Although on this graph, it doesn't really seem it. You're right, we probably should go this way, right? Because G's over here. But the heuristic was given to us already. So C is in the right direction towards our destination node because of the heuristic. So now we mark C as our lowest distance was traveled. So we look at all of C's neighbors. It has the start node, so we don't check it. And it has E, which has a distance of 22. So now we look at the distance from A to E, being 66. We mark that down here. And the sum is then 86 here, with the previous node being C. So C is now visited. Which has the lowest distance traveled plus heuristic? It's E. It's still lower than B, so we want to look at E. E could go back to A. It could go to B. It could go to D. It could go to F. It goes to so many places. So let's do F first. So distance from E to F is going to be 66 plus 15, which is going to be 81. So to F, 81. 81 at A is 89. And it came from E. Cool. That's F. So let's look at B. Well, B's going back. It's not going to be minimized. Good thing about it. A to B is 20, but then A to E to B is like way more longer. So we're not going to look at that. To D, it will be whatever the weight of E is, which is 66 at 62, which is going to be 128. And it doesn't have anything here, so we do that. 128, and it's going to be 198. Previous node E, and E is fully visited, right? So look at the nodes which have the lowest non-visited distance traveled plus heuristic, and it's F, right? F is still lower than B, or the chances. So we look at F, and it connects to E, which is already visited, so we don't really want to worry about that. And it also connects to G with a weight of 9. So we then do 81 at 9, which is 90. And we add the heuristic of 0 to 90, previous node being F. So we can mark F as visited. Now, this is where A star is really becoming apparent to be better than Dijkstra's. We didn't see it in the simple example, but now, G has the lowest weight of unvisited nodes. It has the lowest distance plus heuristic of 90 compared to 198 and 100. So now that we've reached our destination, we just stop. We don't have to check B and D because obviously we don't care about B and D. We're going from A to G. That's what the question's are asking us. So it stops a lot earlier. However, this might not be the most efficient path. Why? We haven't checked B and D. B and D might actually lead to a path that is less than 90. Oh, what did I just do? That is less than. What the hell's going on? That is less than. Okay, I give up. It's. What's going on? Okay, I fixed it. That is less than 90. Jesus Christ. With the path being G to F to E and E to C. Look at this. Jesus. C to A. The path is A to C to E to F to G. And this travel is 90. So quite a nice paper. And I can get this paper up, look at the mark scheme. LCL pass. Computer science. And we can go over the mark scheme just as a comparison. Let's look at the Dijkstra question. So here we have, and this matches what I have quite nicely. If we can just go like this, bang, 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 bang. So yeah, marked up here, but it doesn't really matter. You'll get the marks for this if you leave this as blank because it literally doesn't matter. As long as you mark this as 90 and 0, which is what we did. And then we have all of this and traveled and stuff, and it matches the mark scheme. Nicely done. So that is how A-star and Dijkstra's work, but you could also get asked some comparison questions between them. So let's just go over the highlight the notes that we went through, right? So we have Dijkstra's algorithm is more accurate than A-star. It always finds the shortest path. Always. It finds the shortest path at every node in the graph, given a start node. But Dijkstra's is less time efficient. It finds every node, which meaning that it's gonna work for longer. It's gonna take longer to finish, right? Because A-star doesn't ensure every node is visited, right? It stops once you reach the final node. But that doesn't mean that it's the most efficient path because those nodes that you haven't finished might actually lead to a better path, but your heuristic might have just been horrible. So what that means is A-star is quite dependent on how good the heuristic is, right? If the heuristic is really is inaccurate, it will lead you down a path which actually doesn't really minimize it at all if your heuristic is misleading you completely, right? That makes sense because when we look through the algorithm, we're relying on the heuristic on the direction we need to go in. So you could get a long form answer comparing the usage of Dijkstra's and algorithm. That's your algorithm in A-star in a given scenario, a very long 9 marker. That would be quite mean because you'd have to apply it quite strongly to the scenario. If you see here, you would describe how the functions work, how the algorithms work, and what they do, and then apply it to a given scenario. And then the more short form questions we'll get comparison questions on is, do you need time efficiency or do you need accuracy? In the context of the scenario, is it better to sacrifice accuracy or is it better to sacrifice time efficiency? Do you need it to take no time at all and you don't really care about accuracy? Or something where accuracy is very, very important? Maybe like a government filing, you need pure accuracy. You're willing to sacrifice a couple of days for this because you need pure accuracy. Or maybe it's a classroom where you need to be quick. You need to be quick. You don't really care about accuracy. You need to be quick for the kids. I don't know. And then you also want to consider, are good heuristics possible for this problem? Are you able to calculate good heuristics? Because A-star relies on good heuristics. If you're not given good heuristics, A-star will be quite inaccurate in finding the shortest path. So that's the pathfinding algorithms. Not really a quick video, 24 minutes, but that's all you can get asked about those two algorithms. So I hope you enjoyed the video.